All right, it's 7 o'clock. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good. Good, good. Second day of class. Hopefully, everyone's having a good first week. I'm hoping the weather cools down a bit, although it feels like the AC is actually working today. Didn't feel like that on Monday, but also there's less people here, which I think helps. Okay, so plan for today. We're just going to continue with the lecture that we started on Monday. So Monday we started kind of kind of like our crash course review of fluid mechanics. So we'll continue with that. I think all of this week will just be kind of review. We'll probably look at things from a slightly more rigorous mathematical perspective than maybe you learned in your initial fluids class. But first couple weeks of this semester will just be kind of review of fluids. Okay. Now fluids, like I said, is a prereq for this class, but I know probably for some of you, maybe it's been a while since you've taken fluids. And so we're going to review some fluids before we start getting into the new stuff, maybe probably around week 3. So, okay. Okay. Any questions I can answer before we get started for today? Okay. So I haven't posted the first problem set yet, just because first couple weeks is just review. You can probably expect the first problem set to be posted early next week. Okay. All right. So let's go ahead and pick up where we left off. And so I'm just going to scroll up here, just because we were kind of going through this. Okay. Okay. So the point at which we were looking at the review, or the point in our review, we were looking at all the different fluid properties, right? So last time we kind of introduced just the concept of what a fluid is. And so the fluid properties are kind of our way to, these are all kind of measurable parameters that we can use to basically assess a fluid, okay? And so we talked about velocity. So velocity is pretty straightforward, but it's also probably the one that we are going to use the most, okay? And then next we start talking about acceleration. Okay. Now, acceleration itself is not that interesting. And so, you guys have been familiar with the concept of acceleration for many, many years. I think what's interesting about acceleration in fluids is how we actually describe it. Okay. So kind of the last thing that we kind of that I wrote down at the end of class on Monday was this expression here at the bottom. Okay. So this is what we call the material derivative, and it's a concept that we will see, much, much more in this class. And so, I did want to spend some time now kind of explaining what that actually means. Okay. Okay, so material derivative basically says that if you're going to take the derivative of something in a fluid, so in this case, we're taking the derivative of velocity, but this material derivative can apply to any property as well. What we're seeing is that there are multiple different terms that we have to take into account. Okay, it's not simply just the derivative with respect to time, right? Because remember what we said last time is that every fluid property here is a function of multiple variables at the same time. Okay? Okay. So whenever we're talking about anything with fluids, we're talking about changes in space and time. Okay. And that goes back to the whole idea of the continuum assumption, where we're not following just individual fluid particles, we're looking at kind of the fluid as a whole, right? And so as we kind of move from one location to another, or maybe we don't, maybe we just look at a fluid property just at a fixed point in time, changes can occur in all of those things. Okay. And so when we take the rate of change, right? So in other words, when we take the material derivative, we have to account for changes in all of these different dimensions. Okay. Okay. So let's break down the material derivative a little bit more. Okay. Okay. So let's define material derivative. So material derivative tells us the rate of change of a fluid property in the continuum assumption. Okay. So the material derivative is how we quantify it. Okay. Now, remember, in the continuum assumption, like I just mentioned, we can have changes in space and time. Okay. So let's express that in the material derivative, okay? So, I know we just finished talking about acceleration, but, let's consider a property f, okay? So this f can be is some generic fluid property, right? And so we can set f to be equal to the velocity. If f is velocity, then taking its material derivative will give us acceleration. Okay? Okay. So I'm introducing this F not to confuse you, just because I know, sometimes in this class it's going to feel like alphabet soup, and sometimes there are lots of different variables and letters at you. But this is just to show you that the material derivative can be applied to anything. Okay. Where F, right? If we're in the continuum assumption, F is going to be a function of all three spatial variables, X, Y, and Z. Okay. Right? And so just moving from one location to another in the fluid field, the value of F can change, right? Otherwise, and this is how we express it, and is a function of time. Okay? Okay, so let's break down the material derivative, or let's kind of derive how we arrive at that statement from above. Okay. Now, before we do that, we have to make note that, because we are in a moving fluid, right? When you move from one point to another, the spatial variables also are functions of time because of just the fact that we're in a flowing velocity field. Okay. And so another way to write this is that f is a function of x, which is a function of time, function of y, which is a function of time, z, which is a function of time, and then time itself. Okay. Okay. Right. So I know that statement seems a little bit strange, but it's just due to the fact that we're under the continuum assumption, and because the fluid is flowing, right, then our positions are going to be dependent on how we move with the flow. Okay, I think that's probably the easiest way I can kind of state it. Okay. Okay. So that means if we were to take the time derivative or the derivative with respect to time of f, okay, which is what we aim to do with the material derivative, right? Because each of the spatial coordinates also depend on time, we need to perform some chain rule in order to make sure we carry that time derivative all throughout. Okay. Okay. You probably never thought that you see chain rule ever again outside your math class, but here it is. This is why it's important. Okay. All right, so let's go ahead and do just that. Okay, so remember the chain rule basically says that if you're taking the derivative of a function, which is a function of another variable, and that variable is a function of another variable, you have to carry that derivative through and multiply those derivatives next to each other. Okay, that's a very complicated and terrible way to explain it, but I think you'll see once I kind of write it down, it's more straightforward than you would imagine. Okay. Okay, so if we were to take the derivative of f with respect to time, okay, so we have df dt. Okay. And we know f here is a function of four variables, right? It's a function of x, y, z, and t, right? So let's start with that. So let's start with x, right? Right. So first we have partial f, partial x, okay, because f is a function of x, right? But then since x is a function of time, and we're taking the derivative with respect to time, due to chain rule, we have to multiply this by the derivative of x with respect to time. Okay. So the first term in our chain rule material derivative expression is partial f partial x times partial x partial t. Okay. And the reason I say it, it's simpler than you think, simpler than you remember, right? If you just do, this kind of imaginary stoichiometry thing where you say we have partial x in the denominator here, partial x in the numerator here, those cancel out. In the end, we get partial f partial t, which is exactly what we have on the left-hand side. Okay. So in terms of units, right, everything should work out. Everything should have the same units, right? Although we have to be explicit with these derivatives, because with derivatives, you can't just cancel out numerators and denominators like that. Okay. But I wanted to kind of show you that, that where each of these terms kind of come from. So each of these terms here should have the same units of partial f, partial t. It's just that the way that we arrive there is going to be different depending on the variable that we're taking derivative of at that moment. Okay. Okay. And so we have the exact same thing for y. So we have partial f, partial y, multiplied by partial y, partial t, due to our chain rule. Okay. Same thing with z. So partial f, partial z, partial z, partial t. Okay. right? So those are all the derivatives of f with respect to the first three variables, x, y, and z. And then we have the derivative of time, right? And so that's just partial f, partial t. Okay. Okay. So kind of first step of the derivation of the material derivative, it's mostly just a straightforward application of the chain. Okay. Next observation that we'll make is, we'll go back to kind of this definition right here, or kind of this assumption, where the spatial variables kind of represent our motion with the fluid, right? That means if we look at all of these variables here, so partial x, partial t, partial y, partial t, partial z, partial t, okay? So since x, y, z represent position in the moving fluid, okay? Again, due to our continuum assumption, which states as such, right? If we take the derivative of position, right, we get velocity. Okay. And so the last step in the material derivative is just to simply replace all of those partial derivatives of x, y, and z with the corresponding velocity components of the flowing fluid. Okay. All right, and so we have our material derivative df dt is equal to u partial f partial x plus v partial f partial y plus z partial f partial, or excuse me, w partial f partial z plus partial f partial t. Okay. Where u, v, and w, these are the x, y, and z components of the fluid velocity. All right, so that expression there is our material derivative, which, again, we applied it to just a generic property f, but if you replace f with the velocity, then that gives us our acceleration, which we had above. Okay. All right, any questions on the material derivative here so far, how we got here? Okay. Okay. And so, one last thing I'll say about this to wrap it up, just to kind of connect this to the last point that I made. Okay. So usually we'll group these terms, according to what they represent, right? So there's kind of two parts of this material derivative. There is, and let me use a different color. Let me use blue. Okay. There's these group of terms right here, right? So all the terms that have the fluid velocity next to them. So u partial f partial x, v partial f partial y, w partial f partial z. Okay. You can see that all of these kind of represent kind of the same thing, just in different directions. And so these group of terms, right? They obviously represent how the property f can change with space and the moving fluid. Okay. And so these group of terms here, they have a name. So, just to make it easier to refer to them, we call these the convective terms usually. So hopefully that term is, rings a little bit of bells, right? So you probably heard of the concept of convection before, maybe in your fluids class, but almost certainly in your heat transfer class, right? So convection, remember, is kind of just the idea that things can change or things can get transported in a moving fluid, right? So very easily, you can think of F, right? One example of the material derivative is actually applying this to heat transfer. So if you plug in, like, say, temperature of a fluid in for F, then this expression here gives you the rate of change of temperature in a moving fluid, right? So temperature can change with time. It can also be convected and moved along in space by the moving fluid, okay? All right, and then the other term here, kind of the term that's kind of all by its own, but it's the only term here that is just purely a derivative with respect to time. So this, of course, represents how F can change with time at a fixed location. Okay. So this also has a name that I will be referring to, quite a lot in this class. This is known as the unsteady term. Okay. Okay. So a little bit of a detour. In fact, we kind of just took a preview of our next set of lecture notes, which is fluid kinematics. But I think if you're talking about acceleration, you're talking about rate of change of a fluid property like velocity, then you can't really have that conversation without talking about the material derivative. Okay, so definitely hang on to this idea of the material derivative. This is something we'll come back to quite a bit in this class. Okay. Okay. All right. So anyway, back to our regularly scheduled programming. So let's go ahead and continue on with our survey of the different fluid properties. Okay. Okay. So next one I want to go over is the pressure. Okay. Pressure is another unique concept that occurs in a fluid. There's the idea of a pressure inside a solid, there are things that form within a solid. It could have a structural stress, but it doesn't perform the same function as pressure, mostly just because fluids flow. Okay. Okay. So what is the pressure? So the pressure, you might know pressure as having units of force per unit area. Right? So that's the units of pressure. And so whenever you have a fluid, right, a fluid is always going to exert some kind of pressure force on whatever object that is within that fluid. Okay. Okay. All right. So pressure is quite interesting because there's multiple different sources of the pressure forces within a fluid. Okay. So probably the one that you learned a lot in your first fluids class and probably the first thing that comes to mind when people think of fluid pressure is the idea of hydrostatic pressure. Okay. Now, we won't be dealing with hydrostatic pressure all that much because, like the name implies, hydrostatic pressure is the pressure in a static fluid. So for the most part, in this class, we'll be looking at fluids that are actually in motion. Okay. But hydrostatic pressure develops due to gravity, essentially, right? And so the deeper you go within a fluid, right, you can imagine that all the fluid particles on the bottom layer have to support the weight of all the fluid above it. Okay. Okay. All right. So for instance, if you have let's say a pool of fluid here, right? Right, like that. One of the first things that you learn in your introductory fluids class is that the deeper you go in a column of fluid like this, the higher the pressure is going to be. Okay. So let's that, if you compare location one, location two, right? Location two is going to have higher hydrostatic pressure because it has to support the weight of all the fluid that's above it. Okay. Right. Because fluids have weight, right? And so, we talked last time about density. Um, and so, there has to be some kind of internal force above it to support that weight, just to have, just to maintain static equilibrium. Okay. Okay, so that's one source of pressure, but I only just mentioned that just as a review. But again, we're not going to be doing much with hydrostatic pressure in this class. Okay. The other way to think about pressure, or the other reason that pressure develops in a fluid, specifically in a moving fluid, is that pressure often is a driving force causing fluid to flow. Okay? Most notably in internal flows, and so flows that are kind of bound on all sides, so flow in a pipe, right? Pressure is often the driving force that drives that flow. Okay. And so if you have a pipe like this, right? And you have flow that's going from, let's say, left to right, right? The thing that drives this flow often is a change in pressure, right? And so the pressure on one side here, we'll call P1, pressure on the other side, P2, right? In order to drive the flow from left to right, the pressure on the left has to be greater than the pressure on the right. Right. So this is kind of the main principle that drives pipe flow, right? So if you spend any time, looking at the plumbing system within your house, right? A lot of that is just kind of manipulating the water pressure in your house in order to drive the flow to where it needs to go. Okay. And oftentimes, pressure gradients like this are generated by some kind of mechanical device, so like a pump or something like that. Okay. And not eat and this idea that a flow that liquid or a fluid will go from high pressure to low pressure is not just limited to pipe flow. This is something that's true in general. And so usually if you want to get fluid to go from one place to another, you can somehow develop a way or kind of find a way to generate high pressures in one region, and that'll drive fluid to another one. Okay. Pressure kind of behaves very similarly to, how you understand heat, right? So heat, we know, always goes from high temperatures to low temperatures, or just gravity too, right? And so, just because we live in a gravitational field, right? Objects will tend to fall from high elevations to low elevations. Okay. So pressure kind of plays the same role, although for fluids, it's a bit more complicated. This isn't always true. There are times when fluids can flow against an adverse pressure gradient, and so it can go from low to high pressure, but we'll get to those situations kind of later on and why that happens. Okay. Okay. Any questions on pressure? Okay, good. All right, next one. Let's talk about density. So this semester, I'm also teaching an undergraduate fluids class, actually the intro class, and so sometimes I may get mixed up in terms of what I discussed there and here, but I don't think we went over density all that carefully last time. Okay, so thankfully, density is it's pretty easy to understand, and so density of a fluid, density of solid, kind of have the same intuition, the same understanding. Okay. Right, so the density is basically our way to express the mass of a fluid. Okay? So it characterizes the relative mass of a fluid per unit volume. Okay? So density is you can think of it as a ratio. So the expression for density, or first of all, the symbol for density is this symbol called rho. Okay, so rho looks like kind of a P with kind of a slanted kind of tail there. Okay, so density of a fluid is just the mass of the fluid, the mass of a certain, volume of fluid divided by the volume that the fluid occupies. Okay. So density is used a lot in our equations for fluids because of the flowing nature of fluids, it's often hard to isolate just a fixed mass of fluid. Okay. That's kind of something we talked about on Monday with the continuum assumption. And so when we want to express, the mass of a fluid, oftentimes we use density because density is kind of irrespective or kind of doesn't depend on the specific amount of fluid we have. It's what we call an intensive property. Right? So it's a property that doesn't depend on just the amount of fluid. It's something that's just kind of inherent to the material, right? You can think of density as like a material property, so something that's just inherent to the type of fluid that you're okay. So water has a particular density, right? Doesn't matter if you have water in a huge swimming pool, water in a water bottle, right? Granted, assuming that they have the same chemical composition. I know, pool water has chlorine. You don't want to be drinking that. But they approximately have the same density because they're made up of water. Okay. Same thing with a more dense fluid like maybe like honey, right? So honey, whether you have a small bottle, big bottle, they have the same density, right? Because whatever mass that it has, you divide it by the volume. Okay, so density pretty straightforward. Last one that we'll go over, and it kind of segues into the last part of these lecture notes is viscosity. Okay. Which in a lot of ways is kind of the star of the show because that's kind of the point of this class is viscous flow. Okay. Okay. And so just like I mentioned in the slides on Monday, viscosity, which also is an intensive property, represents a fluid's tendency or fluid's ability to resist flowing. All right, so I think that's probably the most kind of plain language explanation of viscosity. Another way to think of viscosity is viscosity kind of plays the same role as friction, right? So kind of all the intuition, all the understanding that you have about friction that you gain from your previous classes in solid mechanics or just basic physics, right? Viscosity kind of plays that same role. It's not quite the same because friction is not really an intensive property. Friction depends on a lot of different things. Friction's actually pretty complicated if you actually get into the weeds of it. But if you think of how friction works for solids, right? And so if you were to try to if you were to take an object like this phone, if I were to try to push it across the table, right? It doesn't matter how much force I push it with, right? Eventually it's going to come to a stop, right? Because there's friction in between my phone and the surface, right? That's going to impede the motion of the phone and then eventually it's going to come to a stop. Okay, so viscosity kind of plays that same role. It kind of resists motion. Okay. Okay. So I think that's a pretty good way to kind of understand viscosity for now. But if you were to kind of look at kind of a more rigorous definition of viscosity in terms of its mathematical kind of representation, okay, viscosity actually represents or it shows the relationship between shear stress and strain rate within a fluid. Okay. All right, so the kind of the equation for this is tau is equal to mu times du dy. Okay, and granted, this is a very simplified form of this equation here, but I think it's kind of enough to get the point across. Okay, so like I said earlier, this class can be alphabet soup sometimes. I throw all these different symbols at you, but let's define everything here. So this tau, okay, this tau represents a shear stress. Okay. So remember, stress is essentially a force, and so that tau there has units of force per unit area. Okay. This derivative quantity here, right, du dy, this represents a strain rate. Okay. And then this mu that's kind of in the middle, this here is our viscosity. Okay. So you can see from this equation here that the viscosity kind of forms that kind of mathematical relationship between these two quantities here, right? So the shear stress is equal to the viscosity times the strain rate. So you can almost think of it as kind of like a scaling constant in between those two properties, okay? Okay. So let's give this a bit more context. And so, we're going to get more into the strain rate, probably later today once we start talking more about fluid kinematics. But, let's give a bit more context to shear stress and strain rate. Okay. So strain rate, right? One way to think of the strain rate is that strain rate kind of represents how quickly the fluid is flowing. Okay. It's not quite that, but I think for now, I think that's an adequate enough definition. The shear stress, right? Remember what we said, shear stress is an applied force per area. So shear stress here represents how much force that you're applying to the fluid. Okay. So in other words, if you kind of bring those together into our equation here, we can see that on one side of the equal sign, we have the force that's required to make a fluid flow, okay? And on the right side, we have the speed at which the fluid is flowing, right? And the thing that connects them is the viscosity, right? So if you kind of think about it from this way, right? Right. So viscosity is kind of the linchpin in this whole situation here. So if you have high viscosity, right? So mu is some high, relatively high number, right? Then what that tells you is that in order to get the fluid to flow, you have to apply a lot of shear stress. Right? And that comes just straight from the equation, right? And so, if your viscosity is a high number, right, and you want to have a certain amount of fluid flow or strain rate, that means your shear stress also needs to be high to account for that, right? Because a high viscosity multiplied by higher strain rate is the higher shear stress. Okay. Where on the other side, if you have a low viscosity, I apologize, it's getting a little bit messy. Hopefully you guys left a bit more space. Okay. A low viscosity means that you can have higher flows with less amount of shear stress. Or in other words, you don't need as much shear stress to cause the fluid to flow. Okay. All right, so you can see from this equation here, even though, we haven't quite gotten to the full definitions of shear stress and strain rate, even at a rudimentary level, you can see that viscosity here kind of represents that threshold or the scaling factor that's needed to cause fluid to flow, right? So higher viscosity, more resistance to flowing, right? And this equation kind of represents exactly that. Okay. All right. So again, so viscosity, we're going to come back to the concept of viscosity. It kind of plays a role in everything that we do in this class. But I think for now, I think this is a good stopping point or a good way to kind of understand it, just to kind of help introduce the other. Okay. Any questions on viscosity? Yes.
Just a comment. You could really relate it to Hooke's law a lot with the F equals kx.
Yeah.
Same rules apply as well with the higher K, lower K. And it's interesting too with the shear stress, that's the force over area, F equals kx. And then x, the elongation, x, your distance, the strain rate. So it's just similarities.
Yeah, no, absolutely. That's a great observation. And then you could even connect it to the Hooke's law in solid mechanics too, which is stress is equal to Young's modulus times strain. This is actually a very, very similar expression to that. So yeah, no, that's a great observation for that, for sure. Mhm. Yeah, the only difference here is that there's an added dimension of time because strain rate actually has its velocity, it's a derivative of velocity with respect to space. And so viscosity also has that time factor to kind of cancel that out. But it's almost the exact same idea of that.
Is that where they derive it from, maybe? Like from the
Yeah.
beginning?
Yeah. So the origins of viscosity, kind of is derived in kind of the same way. So if we were to derive this equation from first principles, like a conservation of basically momentum, then you would arrive in the same way. Yeah. Yeah. Great observation. All right. Any other questions on viscosity here? Okay. All right. So one last thing I want to mention before we get to fluid kinematics is let's talk about when viscous effects are relevant. Or important, I guess you can say. All right. it seems kind of a strange question to pose, right? Because viscosity it's not like viscosity ever goes away. So viscosity is kind of always present, right? And so just like if you think about solid mechanics, friction, air resistance, these are things that are always there. And so, what do I mean, asking the question when viscous effects are important? Well, right, whenever you have a moving fluid, in reality, there are multiple factors that are kind of competing against each other. Okay. All right, so the first one, right, since we just kind of finished talking about it, is viscous effects. Okay. Okay. So what do I mean by competing factors? So viscous effects, when we talk about viscous effects, we're specifically talking about the shear stresses that form within the fluid as a result of the presence of viscosity. Okay. All right, so that's one of the competing effects. The other one, right? At least, and these are not the only factors, but these are ones that are kind of in direct competition with each other. Okay. The other kind of category of effects that can occur in a fluid are what I call inertial effects. Okay. Right. So you can think of inertial effects as the momentum of a fluid, right? And so, right. And so just like a solid object has momentum, right? So you have like a car that's moving at a certain velocity, right? That has a certain amount of momentum just because of the speed that it has. Right? Okay. All right. So the reason I call these competing effects is that oftentimes these have, their vectors are often going in opposite directions, right? So remember, viscous effects at the end of the day, effects represent an impedance to flowing, right? And so if you have fluid that's going one way, right? Let me draw our pipe one more time. Okay. So let's say you have a fluid in a pipe that's going from left to right, right? There is going to be viscosity in this pipe just because it's a small pipe, right? Viscous effects are going to attempt to slow down the flow, right? So viscous effects are going to go in the opposite direction of the fluid. Okay. So the shearing forces are going to be impeding it, just like friction. Okay. So oftentimes, these two, effects that I'm kind of giving a very broad term to, they are kind of in direct competition to each other. Okay. Now, usually what tends to happen, when you have competing effects is that when one effect has a much higher magnitude, it kind of dwarfs the effect of the other one. Okay. So in other words, when inertial effects are very high, right, then that kind of dwarfs any kind of friction that may occur, right? So think of like a solid object with a lot of momentum, right? So think of like a F-150, right? A huge truck, right? So if that's barreling towards you at like 60 miles an hour, right? There's friction. Friction is there. It's going to be slowing the truck down, but it's not really going to be doing all that much, right? You're still going to be, it's still going to hurt a lot if you get hit by an F-150, right? Um, and so it's the same thing for fluids, right? And so for flowing fluids, if the inertial effects are very high, then that kind of dwarfs any kind of effect or any kind of impact that the viscosity is going to have. Okay, and vice versa as well. Okay. All right. So of course, the operative word in this statement is high, right? So what do I mean by high? How high is high? How do we actually quantify that? Well, it turns out there is a way for us to actually quantify this, and it's through the use of something called a non-dimensional number, which is something that fluid mechanics love. And so there's a ton of non-dimensional numbers in fluids, right? And so the one that we're going to be concerned about a lot, that we're going to compute a lot, probably the one that you've already learned, is the Reynolds number. Okay. All right, so the very famous Reynolds number is given the symbol Re. Okay. Right, so the definition of the Reynolds number, the way that you compute it is that you take, in the numerator, you take the density of the fluid multiplied by some characteristic length, multiplied by some velocity, okay? And then you divide that by the viscosity of the fluid, okay? So rho times L times U divided by viscosity, okay? So I think the only symbol here that we haven't really defined here is L. So L here is some characteristic length. All right, and if you work out the units for this, and so you multiply all the units in the numerator, well, the denominator is only one unit. You'll see that they cancel out. So this Reynolds number is dimensions. Okay. Okay. So that's probably something that you covered in your introductory fluids class. But if you look at the combination of terms in the numerator and denominator, they represent this exact kind of competition that we kind of talked about before, right? Because in the numerator, right, we have density, where we know density is a representation of the fluid's mass. We have velocity, which is a representation of the speed, right? And we have length up there just to kind of balance out the units. Right? The top there is essentially a measure of the fluid's momentum, or in other words, its inertia. Okay. Whereas the denominator there is very straightforward. It's just straight up viscosity. And so that you can think of the denominator as representing viscous flux. Okay. Okay. So Reynolds number, just like every non-dimensional number that's in fluids, represents a ratio of two competing factors within the fluid itself. Okay. And so if we go back to the original question that I posed at the beginning of the section, right? When are viscous effects important, right? They're going to be important in situations when the denominator of the Reynolds number is large, okay? Okay. And if you think about situations where the denominator is large, right? A large denominator means that our Reynolds number overall will be small, okay? So that's the regime that we're going to be looking at the most in this class. We're going to be looking at low Reynolds number flows. So as Reynolds number gets higher and higher, you're going to look at more inertia dominated flows. That's when you get into the realm of turbulence. We'll touch on turbulence a bit because actually surprisingly viscosity does play a role in turbulence. That'll be kind of at the very end of the semester. But for the most part, we're looking mostly at low Reynolds number flows. Okay. But now you might be asking, right? And in fact, it's still on screen here, so it's actually very, very relevant. But how low is low, right? And so we went from one vague definition to another vague definition, right? So when I say low Reynolds number, that really kind of depends on the situation and the application. Okay. Okay. Now, I hate to kind of leave it like that because that seems so unsatisfying, but it really does depend on, the geometry of your flow, how big your flow is, what are the spatial dimensions, what are we looking at? We're looking at, unsteadiness, lubrication theory, the threshold for low Reynolds number depends on that, okay? And that's true for other quantities as well, right? So when you think of turbulence is on the other side of the spectrum with a very high Reynolds number. But the cutoff for high Reynolds number for turbulence, again, kind of depends on the situation that you're in. Okay. All right. Any questions on Reynolds number? Okay, good. All right. So for the last 20 minutes of class today, I do want to start the next set of lecture notes on fluid kinematics. So we've already done some of it. So we talked about we've already talked about the material derivative, but there's a lot of other kind of concepts in fluid kinematics that we need to look at as well. Okay. So this is the start of the next lecture notes, which again, normally we don't start until next week, but just with all the holidays that we have this semester, we just got to keep trucking, we got to keep moving. Okay. Okay. So what is fluid kinematics? And so fluid kinematics refers to the description of fluid motion. Okay. Which, for all fields of science, this is always the first step of learning a new subject, right? Because in order to kind of analyze something, in order to really learn about it, you have to know how to describe it, right? And so kinematics is that science, the description of fluid flow. Okay. You can think of it as kind of the language of fluid motion, the language of fluid mechanics. Okay. All right, so again, we've done some of this already, right? So all of our discussion about velocity, acceleration, material derivative, kind of all that technically falls under fluid kinematics, right? Because we're describing the motion of fluid, we're describing how quantities change with time and with space. Okay. But let's kind of build upon those ideas. Okay. Okay. So the first kind of topic within kinematics that I want to go to actually kind of is kind of a revisit of one thing that we just introduced was this idea of strain rates within a fluid. All right, so let's come back to that idea and let's kind of give a more rigorous definition of what the strain rate represents. Okay. Okay. So the strain rate of a fluid basically represents how quickly a fluid parcel or a fluid kind of, a section of fluid deforms as a function of time. Okay. Okay. So visually, it's something like this. And so if you were to do, take a snapshot, right? So let's say you have a flowing fluid, it's some kind of complex flow with kind of velocity vectors going all different directions, right? If you were to take a snapshot and say, let's start with a parcel, okay? So let's say we start with a rectangle of fluid, right? So we took just a very quick snapshot in time. We kind of drew kind of a box within the fluid, right? And let's say that, after we kind of take the snapshot, we trace or we tracked the deformation of this parcel of fluid. Okay. Right? You're going to see that that original parcel, right? And granted, like we mentioned last time, if you wait enough time, that parcel will become kind of indistinguishable. It kind of just goes everywhere. But if you were to track this deformation in very, very quick snapshots, you're going to see that that parcel does some very interesting things. Okay. And so in fact, we can kind of characterize the motion or characterize the deformation in several different what we call modes. Okay. So for each mode, I'm going to kind of draw what the original parcel looks like, and then what the mode of deformation actually is. Okay. Okay. So first mode that we have here is, the parcel itself can just grow or shrink in just size. Okay. So the orientation or the shape of the parcel may stay the same. It just may get bigger or smaller depending on the flow. Okay. And so, for situations like that, maybe the parcel kind of grows to a size like this. Okay. So this is what we call elongation or compression. Right? So that is something that can do. The fluid can just straight up just expand, right? Probably not as common for liquids, unless you're looking at supersonic flows, but if this is mostly for gases, right? So gases can kind of inflate and kind of expand much more easily or be compressed much more easily. Okay. Okay. Another form of deformation. So again, let's draw the original parcel here. Okay. Another mode of deformation is that the shape of the parcel itself may warp. Okay. Now the size or the amount of area or the volume of the parcel may stay the same. It's just that the shape of the parcel itself may change. Okay. Right. So in other words, it may look something like this. Okay. So in this mode here, we're not considering elongation or compression. So the amount of area, the amount of volume stays the same. It's just that the shape of the parcel is changing. Okay. Okay. All right. So this mode of deformation is known as shear deformation. All right, so when viscous effects are important, this obviously plays a key role, right? As we kind of seen, right? So shear stress, shear deformation, very closely related to viscosity. Okay. The last mode of deformation. Again, we'll draw the original parcel here. Okay. Another way that the parcel can deform is that, maybe it doesn't change size or doesn't change orientation at all, but maybe it just rotates. Okay, so it basically maintains the same size and shape. It just rotates on its axis a little bit. Okay. So in other words, maybe it might look something like this. So this mode here is called pure rotation. Right? So rotation is actually interesting because rotation is very much a rigid body behavior, right? And so, that's basically what solid objects do. So solid objects, I know, you could have elastic deformation, but in general, if you apply a force and if you look at solid motion, for the most part, you're looking at rigid body rotation, right? So fluids can do the same thing. It's just that, it's a little bit harder to pick out because fluids can flow and deform much more easily. Okay. Okay. So these are kind of the three different modes of deformation. Now, real motion is not just one of these, it's a lot more complex, but basically we can take any kind of real kind of, physical motion and break it up into these three different. Okay. All right. So that's kind of visually what happens, when a fluid parcel starts to deform in response to flow. Now, how do we actually quantify this? Okay. So fluid deformation or fluid parcel deformation. Okay. The way that we quantify is we use what's called the velocity gradient tensor. If you've never heard the term tensor before, tensor is just a way to describe a matrix. Okay. It's actually a more general form, a more general term than matrix. Matrix usually describes some two-dimensional construct, but you can actually have tensors in 3 dimensions. You can have tensors in 4 dimensions. It's as hard as that is to realize. Thankfully for fluids, we don't go beyond 2 dimensions. So, we have just 2D tensors, which are just matrices. But, I just want to give you some trivia in terms of what tensors are. Okay. Okay. So the velocity gradient tensor looks like this. Okay. So we have our velocity. Okay. Where remember, velocity is a vector quantity, and so it has components in the x, y, and z directions. Right. So the velocity vector, remember, has components u, v, and w. Okay. And so we're going to take the gradient of this. Okay. So the gradient, when you take the gradient of something, we use this kind of upside down triangle here, which we call a nav. Okay. So this operator right here is the gradient operator. Okay. All right. So once again, we're kind of pulling from our knowledge of multivariable calculus. Okay. So if you recall, from your previous math classes, a gradient operator takes the derivative of whatever you're taking the gradient of, but you're taking the derivative in all 3 dimensions. Okay. So you're taking derivatives in x, derivatives in y, and derivatives in z. Okay. Okay. Now, the interesting thing is that, with the gradient operator, we're taking derivatives in all 3 directions. but the object that we're taking the derivative of has three components, okay? So we need to take derivatives in three directions of a vector quantity that has three components, okay? And so, we have the gradient operator means that we're going to take every single combination of derivative and component, right? And the best way to do that is to represent it with a matrix. Hence, we call this the velocity gradient tensor. Okay, so we end up with a 3x3 matrix, okay, where we're going to take the derivative of every velocity vector or velocity component in terms of each of the directions x, y, z. Okay, so for instance, the first row is going to be the derivative of the x component of velocity with respect to x, y, and z. Okay, so you have partial u, partial x, partial u, partial y, partial u, partial z. Okay. Right, so three entries, three columns, each one represents the derivative in a different direction, x, y, and z. Okay. All right, second row. Second row is going to be the derivative of v with a y component in terms of x, y, and z. So you have partial v, partial x, partial v, partial y, partial v, partial z. Right. And then last row, of course, is going to be the derivative of w with respect to x, y, and z. So partial w, partial x, partial w, partial y, partial w, partial z. All right. More alphabet soup. Okay. All right, so this is how we quantify it. So, how do we, so, this right here is the quantification of this visual representation up here, right? So how do we kind of connect these two ideas? So how do we connect this kind of visual representation of the different modes of fluid deformation to its mathematical definition? Okay. Well, it turns out that, we can do kind of the same thing with this matrix here. We can break it up into different modes or different components, that represent different types of motion. Okay. So you might be wondering, how do we do that? What do I mean break up a matrix? Well, right, if you recall from your, from your linear algebra class, that you can take a matrix and add it to another matrix, and then doing so, you just add the components together, right? We can do the opposite of that as well. So we can take the components of this matrix and then kind of break it up into several matrices and add them together. Okay. So let's write this out, and that'll probably be the last thing that we have time for today because there's a lot of terms here. Okay, so let's start with our velocity gradient matrix here. So you have partial u, partial x, partial u, partial y, partial u, partial z, partial v, partial x, partial v, partial y, partial v, partial z, okay. Partial w, partial x, partial w, partial y, partial w, partial z. Okay. Okay. So what I'm going to do is I'm going to break this up into three different matrices and add them together, where each of the three matrices represents each mode of deformation that we had above. Okay. So let's start with elongation and compression. Okay. So this one's the simplest one, thankfully, because it's just a diagonal matrix that contains just the diagonal entries. So it's partial u, partial x, 0, 0, and then 0, partial v, partial y, 0, and then 0, 0, partial w, partial z. Okay. Okay, so we basically just took the diagonal entries, and so this here represents our elongation / compression. Okay. So that's pretty straightforward. So, if you look at each of those terms in the diagonal, those are the expansion terms. So, the derivative of the component with its matching direction, right? So u partial x, partial v partial y, partial w partial c. Okay. Okay. Next one. Next matrix is going to represent shear deformation. Okay. This is where things get a little bit fun. Okay, so this matrix is the following. So this matrix is actually have zeros on the diagonal just because we've already done that with the elongation one. Okay. But it has components in all the off diagonals. So this one's going to be 1/2 partial u partial y plus partial v partial x. Okay. Next entry is in the third column of the first row, 1/2 partial u partial z plus partial w partial x. Okay. Okay. Second row, we have 1/2 partial u partial y plus partial v partial x. Okay. So you notice that the entry in the second row first column is equal to this first row second column. So this matrix is symmetric. Okay. Diagonal entry is still 0. And then the third entry on the second row is 1/2 partial v partial z plus partial w partial y. Okay. Okay. The last row we have 1/2 partial u partial z plus partial w partial x. Okay. Next entry is 1/2 partial v partial z plus partial w partial y. Okay. And then last entry in that row is 0. Okay. Okay, so this matrix here, and I'm rushing a bit just because we're just about out of time. This matrix here represents shear deformation. Okay. So you can see it's a bit more complicated, but we only have entries on the off diagonals. Okay. Okay. So when we come back on Monday, there is one more matrix here. So I kind of hate to leave you hanging here, but I don't want to go over any more than I did because I know I went over a bit on Monday as well. So on Monday, we'll go over the rotation matrix, and so that's the last one here, and we'll see that all of them together add up to our velocity gradient. Okay. All right, so thank you guys for coming today. I hope you guys have a good rest of your evening. I'll keep this up, if you guys are still writing it down, and I will see you guys on Monday.
Just like out of the blue, why did they use 1/2? Is that like the geometry of like the shear cutting through the fluid or?
Yeah, so the 1/2 is mostly just because when you add it together with the rotation tensor, it needs to add up to this velocity gradient here. So everything on the off diagonals, yeah, it's mostly just for scale.
Equilibrium.
Exactly. Yeah, you can think of it like that. Yeah. Have a good weekend. Thanks, guys. Have a good weekend. See you guys. William, did you have any questions before I close the call?